Today is all about how we actually make electricity, which is thermodynamics. First law of thermodynamics tells us that energy can change forms. And that's the key to making electricity. We can make electricity out of all different kinds of energy. One of the main ways we do that is to take kinetic energy and put it into what is called a turbine. Examples of this are down at the bottom. Most dams, hydroelectric dams, work this way. As the water flows through the turbine, it spins. Those turbines are engineered to spin at maximum efficiency. Inside of the generator is a giant electromagnet. And you don't need to know a lot of physics to understand this. The technical name is solenoid. So you've got a coil of wires, and you either spin that or you spin the magnets that are inside of it. And when you move magnetic field inside of an electrical field, it produces electricity. The main idea here is that when we look at wind power, hydroelectric, we are using motion of wind or water to spin a turbine to create electricity. Now, that itself is pretty efficient, right? Because we're going from one form of energy directly into another. But this also presents a limit to us. We will not see vast improvements in power generation unless we can find a way to make our turbines and electromagnets more efficient. We've kind of hit a wall, and we can't do it any better than we are right now. Now, someday somebody's going to invent something that has less friction, less loss of energy in that transformation. But right now, this is our upper limit, a turbine generator. 3 types of energy are made that way, but really about 8 types of energy are made this way. Because when we look at how most power is generated in the United States, especially large scale, like a coal plant or a natural gas plant or even a nuclear plant, the whole idea behind these power plants is that we are heating up water to create steam to then spin the turbine. So even though these are not like hydroelectric or wind power, they all use the exact same upper limit, which is a turbine and a generator. Now, this isn't actually more efficient because look at all the energy loss that occurs here. We go from heat, whatever we're using to make the water hot, which then loses a little bit as we make steam. And then the steam has to spin the turbine. So there's energy loss in between each of those steps. Once again, it doesn't matter what we put on the left-hand side. We can use coal. It's very efficient to make heat. We can use gas. Not only is it efficient, but it's cleaner than coal. We can use nuclear. It's incredibly efficient, more efficient than coal or gas, but only in making heat. The true efficiency is the same for all of them because of the turbine. Geothermal, not quite as efficient as these first 3. And believe it or not, some of our solar energy, we don't go directly from solar to electricity. Instead, what we do is we focus a whole bunch of solar energy to heat up water, to boil it, to drive a turbine. So some solar energy even works this way. Once again, the big problem here is that anytime that we're changing from one energy to another, we're losing some. That's the second law of thermodynamics, and that is called efficiency. For example, if we have a coal power plant, when we burn that coal, we lose a little bit of energy right here to make the heat. And then as that heat converts into steam, we lose a little bit of energy. As that steam pushes the turbine, we actually lose a lot of energy because of friction. We're going from kinetic energy into kinetic, but there's still a loss of energy. And then as we go from kinetic to electric, once again, we lose a little bit of energy. Oh my gosh, the potential of the coal is nowhere near the electrical output that we actually get. We're losing the benefits of it being energy rich because we lose so much along the path. I'm about to show you my I think probably my favorite diagram of the entire year. Now, you're probably, don't get too excited because I'm a super nerd. All right. You're probably not going to find this as interesting as I do. We are able to calculate and graph how we use energy in our country. And so on the left, you can see all the different ways that we produce energy. And look at that. The biggest one is actually oil. And oil is used in, over here on the right, you see our sectors, right? The four I talked about the other day. Oil is mostly used for pushing our vehicles around and to create industrial products. Okay, but 36 what? Oh, do you remember from yesterday the word quad? A quadrillion kilojoules. So these numbers that you see are quads. The second biggest is natural gas. Where does natural gas go? Natural gas is an interesting one because look how it splits off. We use a good chunk of natural gas in our power plants to make electricity. We burn it to heat up water to spin a turbine. The rest of it goes to industry, commercial, residential. You might have a gas furnace at home, a gas stove. I actually have gas and electric at my house. The gas is more efficient in the wintertime heating up my house than electric is. Some people have gas dryers for their clothes, and those are also more efficient. All right, so gas to me is the most interesting one because it's used for two different things. And then they're all used for different sectors in small amounts, but the majority of these are going up into making electricity. And look at what happens on the other side of electricity. Of those 38 quads that go in, only 13 become usable in the sector. We waste 25 quads because of our turbines and our power plants. We just throw it away. We don't capture it. We look on the back end of things, and that's just going into the sectors. The sectors themselves lose energy. And you look at transportation, it looks terrible, right? 28 go into transportation, only 6 are actual usable energy. We lose 22 quads that are quote unquote rejected. Okay, industrial looks about half and half. That's not so bad. They're getting the most bang for their buck with their energy usage. Some of that energy goes directly into products. But really, the problem is right here. It's electricity. That 25 quads that gets thrown away. Now, natural gas was the one I want to focus on again because look at this. Natural gas can be used for things like heat in our houses and our buildings, but it can also be used for making electricity, right? It has two really strong purposes that it can do. And that is where we introduce this concept called cogeneration. Co means together, and generation means to generate energy. Well, that top statement is right out of the AP guide. So they're going to ask you about cogeneration for sure. Cogeneration occurs when a fuel source is used to generate both heat and electricity. We're starting to do this in places like landfills. Landfills, when the material decays, it produces natural gas, methane. And so we catch that now. We catch the methane coming out of the decayed garbage, and we can then burn it to produce electricity and heat. In the old days, we've got our electric power grid, and then we've got our boilers, which make heat, right? I'm thinking about my house. I use heat for my furnace, but I use electricity that comes from a different source. And so that is two different types of energy having to be transformed. But modern efficient systems, you could have one of these installed in your house. They use the example of a greenhouse, which makes perfect sense. It's called a CHP system. CHP means combined heat and power. Instead of doing electricity and heat separate, we get it from one source. And one of the best options for this is natural gas. When we burn natural gas, the first thing we get is the heat, which spins the turbine and makes electricity. But we can capture that heat after we spin the turbine, and we can pump that heat into our system to power our furnace. Instead of being 45% efficient, we've doubled it just by capturing the waste energy, the stuff that was on the rejected part of this chart. Okay, finding ways to capture the energy that is being released and wasted. That's the idea behind cogeneration.